So now that we understand word embeddings, let's take it a step further and add positional information. I will tell you in a few moments what the positional information means, but yeah, just to recap, we had input text, we tokenized the input text, created token IDs, and then the previous section was focused on creating these so-called token embeddings. And we only had a very small toy example. And then just to use the actual sizes for our tokenizer, we mentioned our tokenizer has 50,257 words. And so we pass this vocab size to our embedding layer to create it in this size. And now we also scale this a little bit up because before, we had like an output dimension of 1, 2, 3 tokens, which is just for a toy example. Now we are increasing it to 256, which is what we are going to use to train the LLM later. It's a more realistic size. GPT-2 was originally trained with output dimension of, I think, 1024. I'm not quite sure. I would have to double check. But yeah, this would be something that works also well on a small computer, like a laptop, for example. You can always, try larger values if your computer supports it, but I think this should be supported on most hardware for demonstration purposes, but also to make it a bit more realistic than having an embedding size of just 3 dimensions. So we have now 256 dimensions. So if we do that, so we have our embedding matrix that has 50,000 rows and about 200 columns. So that's our weight matrix, similar to what we did before. Now, taking it a step further, we had also the data loader. How does it now come together with these embeddings? Previously, we created these token IDs. So if I just show you this, it's the same that we've covered earlier. So we have a data loader that creates batches of size 8 with a max length of 4. So 4 token IDs per training example. And then we have 8 examples. And so now, how does it actually relate to the token embedding that we have seen in the previous section? So what we do now is we actually convert these token IDs into these embedding vectors. So if I do that, what I showed you earlier is if I take this and I type input IDs, it would create the sample vectors for the simple input IDs that we talked about earlier. But now we are going to use actually the data batch here. So this would be the data batch that we convert, and let's maybe call this token embeddings, and let's just see what happens. And let's actually look at the size of the output here. So you can see now we have still the batch size of 8. So it's now a 3-dimensional tensor, and the numbers correspond to the batch size. So we have 1, 2, 3, 4, 5, 6, 7, 8 rows, 8 examples. Each example has 4 tokens, like 1, 2, 3, 4. But now it's not just the token ID. Each one of those is actually a 256-dimensional vector. So here, each token ID gets converted to a 3-dimensional vector. Now it's a 256-dimensional vector. It's hard to visualize vectors in 256 dimensions, but we can actually maybe print one of those out. So if we take a look at the first one, first batch, first token, this should give us the vector, the 256-dimensional vector corresponding to the first token in the first batch, basically this one. Okay, so now we converted token IDs into token embeddings. The next step is adding positional information. So let me see if I have a nice figure for this. So previously what we've done is we pulled out these embedding vectors from the weight matrix for each input example. And so I previously chose an input that was, I would say, relatively nice for explanation purposes, where each output row looked different. So we had fox jumps over dog. These are token IDs corresponding to an example input like this. And then we pulled out these embedding vectors corresponding to the token IDs from this weight matrix. Now, what happens if we have the same token ID? For example, fox jumps over fox. So here, this token index 2 is the 3rd row in the weight matrix. And so we get, as the result, this row here. But since in the last token ID, we have the same word, the same token ID. It has the same vector. I mean, it makes sense, right? We are looking up the position here. We are pulling out the vector and create the output like that. Now, this is fine, it would work, but we could actually add some more information to it. So to provide more information to the LLM, depending on where this word is located in the input, we can create so-called positional embedding information. There are different ways you can do that. So GPT-2 used a very simple way. It used a second embedding layer. There are nowadays other ways, for example, using rotational positional embeddings. If you're curious about those, in the bonus material on my GitHub repository, I implemented also Llama 3.2 from scratch. It's more advanced and more complicated, and it's not as nicely described as in the book, but they use something called rope embeddings that I also implemented here. But GPT is, fortunately much simpler in this case with the embeddings. It's using simply a second embedding layer. So let me actually show you how that would work. So we are using the same embedding class we used before, but now we have a token embedding layer. In addition, we have now a position embedding layer where we add positional information. So the goal will be, maybe I have a figure. Yeah, I do have a figure on that. If we have input embeddings like this, the goal is to have a second set of values that we add here. So positional embeddings that we add. So we have, token embeddings. So to step through this figure more slowly, I chose the same token embeddings for each example here, just to keep things simple. So if we have just input that consists of the same word, like fox, 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 for example, the token embeddings would be the same in all the cases, but then we add positional information on top of that so that the actual input embeddings look different depending on where it's located. Now I'm using these very nice numbers where it's easy to read those numbers. In reality, these are all starting with random numbers, so it doesn't look quite as nice. But these numbers, the positional embedding numbers, they also get optimized automatically later during the LLM training. So they are random numbers to start with, and later they will get optimized similar to the token embeddings. So here, I'm creating a second position embedding layer essentially. And then what I'm doing, so here is the max length. So the max length is how many inputs are supported. In this case, we only have 4, right? So we had a max length of 4. 1, 2, 3, 4. It can only support 4 input tokens. In practice, this is a much bigger layer. So for simplicity, we just keep it small. For visualization purposes and just simplicity. Later, when we train the LLM, we will actually use much larger values. And then what we can do is we can use torch A range. So A range is creating in sequential order values here, 0, 1, 2, and 3. So 0, 1, 2, 3 is just a tensor, it's a placeholder tensor for the positions. Position 0, position 1, 2, and 3. And we have this position embedding matrix. And it's a similar matrix to what we had before. Oops. And then when we are calling this with our A range, what it will do, it will just pull out the values like in sequential order here. So you can see it here. So it's just getting me the values here. And that is all that is really happening in this positional embedding layer. And then what we do is we add them on top of each other. So maybe to go before I execute this, this one has shape 84256, and this one should have the same shape. So we can then add them to each other. I have not executed this right here. So I'm sorry. This is actually only for 256 because how PyTorch works, I mean, for efficiency, we don't need to duplicate this over the batch dimension because this one will be added to each batch separately. So what happens is essentially that when we have something like this, the input embedding has the same size as the, The token embedding has the same dimension as the positional embeddings, and then the input embedding will also have the same dimension. So here, the concept is called broadcasting in PyTorch. So let me maybe show it to you like this. So when we do this, we can add these values together. So this is the first example in the training set, and then our positional embedding vector. And this would be essentially similar to doing this, except now we are doing it for all the examples in the batch. But the first example, maybe you can see it here, should be similar. So you can see this one is similar to this one. I mean, this is like a rounding thing, not a rounding thing, a different print representation, but this row is the same as this row essentially, and so forth. So this is just generalizing it over the whole batch dimension. Oops, let me just clean this up a bit. And then when I add them together like before, the shape should be the same as before. So we are just adding this additional position information to it. And so with that, we now have covered the whole input pipeline. So we have input text that we break down into tokenized text. Then we convert it into token IDs. Then we create these token embeddings with our token embedding layer. We create the position embeddings, add them together to get the input embeddings. And so this is all we need to know for now for the data preparation step. Next, let's actually tackle the inside of the GPT-like decoder-only transformer. So what is actually inside the model? One more thing I should say, the embedding layers are technically part of the GPT model, as we will see later. I just draw them outside here because it's a bit easier to talk about it since we already talked about the data loader. But yeah, in the next chapter, we will talk more about the attention mechanism that is inside of a GPT model. So I hope this was useful, and I hope I will see you in the next video.
Get this book at manning.com